Hi class, it's Mr. Dan. In this video, I'm going to show you how to take an old skill that we know and combine that with something new, and we'll end up completing your training on gas laws. So let's dive into this here. What we're going to learn about is something called gas stoichiometry. If you don't remember, stoichiometry is all about quantitative relationships in a balanced chemical equation. More simply put, it's about how much stuff is there in a chemical reaction, and how can we predict what things might happen because of those relationships. So before we go too far, let's take a crash course reminder of what happens in stoichiometry. So if you can remember, we learned how to convert between grams, moles, and atoms or molecules of a chemical. To convert between moles and atoms or molecules, we used Avogadro's number, which is 6.02 times 10 to the 23rd. This says that there are this many atoms or particles in 1 mole of a substance. This is a huge number. To go from moles to atoms, we multiply. Atoms to moles, we divide. We can also convert between moles and grams. We do this by using molar mass, which is a conversion factor using the atomic or molecular mass of a substance. We can find this by looking it up on the periodic table. Either multiply or divide, depending on which way you want to go. Okay, so a quick example. How many grams of water will be produced from the combustion of 10 grams of methane? So this is just straight stoichiometry like we used to do in the past. First thing you got to do, write a balanced equation. All right, so here it is. 1 methane plus 2 oxygens yields 1 carbon dioxide and 2 waters. Next, we want to figure out the mass of turn the mass of the methane into moles. Do that by dividing by the molar mass. Molar mass of methane is 16 grams per mole. You can find that by looking up on the periodic table. Carbon has a molar mass of about 12 and hydrogen about 1. So 1 carbon and 4 hydrogens adds up to 16, or 16 grams per mole. Take the moles of methane and turn it into moles of water. We're going to do that by using the mole ratio. You can see that for every 1 methane, there are going to be 2 moles of water. So we're going to use that ratio. If we have 1 here, that means we need to have 2 here. So if we have 6.25 moles of methane, we're going to need to double that so that we can have 1.25 moles of water. Finally, we want to turn the moles of water into grams, and in order to do that, we want to multiply it by the molar mass. This time the molar mass of water, which happens to be 18 grams per mole, for a final answer of 22.5 grams of water. Hopefully this is just review for you and you already know what I'm doing here. Next, we want to apply this to gases, and so we're going to use a thing called Avogadro's principle to help us get started here. Yeah, the same Avogadro that we just talked about. This time, Avagadro told us that about the relationship between the volume of a gas and the moles of a gas. Here it says Avogadro's law states that equal volumes of all gases at the same temperature and pressure contain the same number of molecules or moles. Maybe a little more simply put, the same number of moles of a gas is equal to the same volume. So same moles, same volume, as long as the gases are at the same temperature and pressure. Okay, we can also find a thing called the molar volume, and when we do this Avogadro's principle at STP, or standard temperature and pressure, we find that the volume of 1 mole of gas is 22.4 liters. So we can turn this into a conversion factor, either 22.4 liters per mole or 1 mole per 22.4 liters. STP, by the way, is 273 Kelvin and 1 atmosphere, or 101.3 kilopascals. Okay, so This is what we would use to find the molar volume of a gas at standard temperature and pressure. This principle always applies as long as the temperature and pressure are constant. If it changes, we can't use this. Let's look at a couple of examples to help us through the way. First example here, combustion of methane. So here we take a look at it. If we draw it out and look at the molecules, we see that what this means as far as the coefficients here, remember this means that we could have one methane molecule combining with two oxygen molecules is going to produce one carbon dioxide molecule and two water molecules. These coefficients represent a ratio. This is the most simple ratio. We could expand this and pretend we had maybe 5 methane molecules. Well, this is a 1-to-2 ratio. So if we have 5 methane molecules here, we need to have 10 oxygen molecules to make this reaction complete. That's going to produce 5 carbon dioxide molecules and 10 water molecules. This follows the same 1-to-2 to 1-to-2 ratio as our original reaction does. We can expand this and say that if we have 1 molecule, 2 molecules, 1 molecule, 2 molecules, this could also mean 1 mole to 2 moles to 1 mole to 2 moles. It follows the same ratio. So in this case, we're dealing with all gases. Let's assume for a moment that all these gases are at standard temperature and pressure. Remember, at standard temperature and pressure, 1 mole of any gas at STP is 22.4 liters. So we're at STP. 1 mole is equal to 22.4 liters. So then what that means is that this 1 mole here, it's any gas, so that's going to be at 22.4 liters. Here, though, we have 2 moles, so that means we need to double the volume. So let's do that. 1 mole, 22.4 liters. 2 moles, 44.8 liters. This is because of Avogadro's principle. All right, now a real example. Here we're looking at the synthesis of nitrogen and hydrogen to make ammonia. By the way, whenever I just say nitrogen or hydrogen, I probably mean N2 or H2. Or if I'm talking about oxygen, it's going to be O2. They only exist by themselves as ions, and so we'll note that they are ions when we talk about them. Okay, so here's our example. 6.0 grams of nitrogen react with hydrogen at STP. How many liters of ammonia are produced? Okay, so how are we going to solve this? What are the steps that we need in order to solve? First thing we got to do, let's organize our data. So go back to the question and read through it carefully and pull out the information that we need to know. We know the mass of nitrogen, 6 grams. We know the molar mass of nitrogen. Now that's not exactly in here, but we can go to our periodic table and find that pretty quickly. We know we're going to need it because we're doing stoichiometry. We always need molar mass when we're doing stoichiometry. We know that this is held at STP, or standard temperature and pressure. And because of that, we know that there's a ratio of 22.4 liters per mole. And it's asking us to find the volume of the ammonia. Okay, what's next? We have to balance this equation. All stoichiometry happens within a balanced chemical equation. So do that now. We get 1 mole of nitrogen plus 3 moles of hydrogen and 2 moles of ammonia. Next, we need to calculate the moles of nitrogen. We're given grams, just like always. If you're given the mass of a chemical and you're doing stoichiometry, go ahead and find the moles. It probably won't be a waste of time. How to do that? So we're starting with 6 grams of nitrogen. We need to divide by the molar mass to get moles. So that's 6 grams divided by 28 grams per mole. It's going to give us an answer of 0.214 moles of nitrogen. Next, calculate the molar volume of nitrogen. So that's where our 22.4 liters per mole are going to come in handy here. So start with our moles of nitrogen, multiply by 22.4 liters per mole, and get an answer of 4.8 liters of nitrogen. But ultimately, we want to find the volume of the ammonia. So next, we're going to use Avogadro's principle to calculate the volume of any other gases. And we want ammonia. So at this point, we know, let's see, I'm going to move over here. At this point, we know our volume of nitrogen. And so we're going to use the mole ratios of our equation to find out how many moles or how many volumes of ammonia we have. Remember from our previous example, if I've got 1 mole here, I've got 22.4 liters. If I have 2 moles here, I've got 44.8. But instead, I've got a different ratio that I'm going to work with. I'm starting off with 4.8 liters. So it's a 2-to-1 ratio. So I'm going to multiply by the mole ratio of 2-to-1. 4.8 times 2 is 9.6 liters of ammonia. That's my final answer there. I've just figured out how many liters of ammonia I've got. It's pretty handy when we're doing gases. We can do a few less conversions sometimes. Okay, so this works really nicely when we're doing standard temperature and pressure gases. But sometimes our gases are not at STP. In fact, most of the time they're not. This still works. Avogadro's principle still works even when we're not at STP. Okay? The only difference is we can't use the 22.4 liters. So let's look at one more example for how this is going to work when we're not at STP. Here, nitrogen and oxygen react to synthesize nitrogen dioxide. How many liters of nitrogen dioxide will be produced if 120 grams of nitrogen are reacted with an excess of oxygen at 350 Kelvin and 1.3 atmospheres? All right. See, this stuff sounds familiar like our stoichiometry days, right? Okay. So, how do we solve this? First thing, let's organize our data. It's written in this word problem. I like lists, okay? Maybe you don't like lists, but I love them. So let's make a list of the stuff that we know or we might need. So we know the mass of nitrogen, 120 grams. We know the molar mass of nitrogen, 28.0 grams per mole. We know the temperature. We know the pressure. And we know what we're looking for. Okay, so now that we know what we've got, what are we going to do next? Oops. Did I miss something here? Oh, well. So, we need to write a balanced equation. Here's our balanced equation out of it, okay? So, nitrogen plus oxygen gives us nitrogen dioxide. This is going to be a 1 to 2 to 2 ratio here. Let's count to make sure. Let's see, 1 times 2, that's 2 nitrogens. 2 times 1, that's also 2 nitrogens. 2 times 2, that's 4 oxygens, and 2 times 2, that's 4 oxygens. We've got a balanced equation. Then we'll get into calculating the moles of nitrogen. We have everything we need right here. We have mass and molar mass to calculate the moles. So 120, we're going to divide by the molar mass and get an answer of 4.29 moles of nitrogen. Next, calculate liters of nitrogen. So remember, we're not at standard temperature and pressure, so we're not allowed to use 22.4 liters per mole. Instead, what we're going to do is we're going to use the ideal gas law. We have everything we need. We now know moles, we know temperature, we know pressure, and we're trying to find volume. So PV equals nRT. Let's first rewrite this thing so that we've got V all by itself. So that is V equals nRT over P. We just divide both sides by P to get rid of it over here and then move it onto that side. All right, now we're ready to put our numbers into our equation and solve. So V is equal to 4.29 times R, which is 0.0821, times 350. All of that divided by 1.3. So we're going to get an answer. Volume equals 94.7 liters of nitrogen. We're only partway there though still. What we're trying to find is the volume of nitrogen dioxide. But we took the hard work now and we found the volume of the nitrogen gas, and so all that's left to do is use Avogadro's principle to calculate the volume of any other gases. So just like in the previous example, we have a mole ratio of 2:1. There's 2 nitrogen dioxides for every 1 nitrogen. So since we already know the volume of nitrogen, we've got it right here, we're going to just double that. Multiply by the mole ratio 2:1. So our final volume of the ammonia is going to be 189.5 liters based off of Avogadro's principle, which states that equal moles has equal volumes. So we can have, if we have 1 mole, we've got 1 volume. If we've got 2 moles, we've got 2 volumes. And that's exactly what we did here. So I hope this is useful for you. Good luck on the homework assignment. And let me know if you guys have any questions. And I'll talk to you guys soon.